Knox Game Design. July 2022. Curves.
Welcome everyone to Knox Game Design for July 2022. My name is Levi Smith. So this month I'm going to be talking about curves. Actually want to be looking at different types of curves and how those can be implemented in a game. So let's start out with how can you use curves in your games? Well, if you have like a tank or something shooting a projectile or a cannon, you can use a curve for that. If you got like a wave beam or something kind of like in Metroid, you can use a curve for that. Jumping, of course, you go up and down. You want that to be in a curve. And also if you're doing paths for characters in your game or like a train track, you can use curves for that. So got 4 different applications for curves. Going to be doing 4 different types of curves, but showing how these curves in themselves are similar. So the first one I'm going to look at, this is the basic parabola that we all probably learned in high school, algebra or geometry. I actually got a picture down here of my TI-85 calculator. So this is probably the first curve or parabola that we all learned is y equals x squared. So basically you take the horizontal axis is your x-axis and your vertical axis is your y-axis. So 1 squared is 1, negative 1 squared is 1, 2 squared is 4, negative 2 squared is 4, 3 squared is 9, negative 3 squared is 9. So that's how you get that y equals x squared right there. So that's all good and well and everything, but if we're shooting a projectile out of a cannon, usually it doesn't go down like a smiley face. It's going to go up and down. So to flip your parabola upside down, basically just do minus x squared. Actually, it's minus, and there could be parens x squared outside of that. So that's going to take it and just flip it upside down. So it looks kind of like the old Lionel Play World commercial. Take your frown, flip it upside down, or maybe that's backwards. So that's great. So now we got it going up and down, but it isn't high enough because it's going to reach a maximum of 0 on y. So to get that to go up, and in all my examples, I'm going to be using a maximum of 4. To get that to go up, to shift it upward, all we do is do y equals that same minus x squared, then add 4 to the end. So that's going to move it up 4 units. So that's great and everything, but maybe our player or tank or whatever, we want it to be at 0, 0. We don't want it to be at negative 4 when it's shooting this projectile. So to shift it over to the right, what we're going to do is within that x squared, we're just going to subtract off 2 from x. So now we got x minus 2, take that, square it, take the negative of that and add 4. So that's going to give us this nice curved parabola starting at 0, going up to 4, then falling back down to 4 on the x-axis right there. So that's great and everything. So I'm going to show a few different approaches of like getting output. So first, just describing it, the mathematical formula. Next, I'll show, usually when I'm trying to like get these values correct and everything, I'll go into Excel. So here's like the basic Excel spreadsheet right here. So we've got X, we're going from 0 to 4. These are all just kind of hard-coded in here. Then these are the 4 different curves that I just showed. Y equals x squared, y equals minus x squared, y equals x squared plus 4, then subtract off the 2. So there's the formulas in Excel. And here's the different curves that we have right there. So that's all well and good. That's just showing, yeah, these are the values. These are the values that we're expecting to come out of our curve. Okay, so here's the example right here. Going to be doing this in Monogame again, C#, but this could also be done in SDL, Allegro, or whatever. I'll leave that as an exercise to everyone out there to do if they choose to do that. But I like Monogame just because it's free and open source and anybody can download and use it. So yeah, basically just have this game manager class, and it has it flips between these different screens. Each screen is one of the curve types in the examples. So I got the 4 different screens that we'll be looking at. As always with Monogame, we're loading in the content right here, just the graphics we'll be using. An update, which basically just calls the update for the current curve that we're looking at. Right here, we got screens, current screen update, and passing the game time. Then we got our draw, so that's also going to pass to the screens draw method right there. So the screen class is just basically a simple super class. It's just going to draw like the axis and everything. Actually, the numbers on the axis and some output information. Really doesn't do anything else. I spent a lot of time working on this scale point method right here, getting it correct. So this example, when we're doing the programming, it's going to be 1280 pixels wide by 720 tall. But I want all the coordinates to be like from -8 to +8, -4 to +4 on the y. Just to keep things simple. And also I'll flip, typically y in pixels goes 0 to screen height going down, so I basically flip that upside down. That's what this scale point does right here in screen. So basically each of these screens is subclass. So here I have our basic parabola. Got a x-min -4, x-max 4, a current x and a current y, the speed that this thing's going to run at. And then I've got the 4 different functions implemented. So on our update, we're just going to move at a constant speed on x from x-min to x-max, multiplying the speed times the elapsed time. That would be delta time in Unity and other languages. So yeah, basically we got 4 different functions that are shown on the on the presentation slides. So the first is just going to have y set to 0, constant 0. The second one, we're going to have y equal to the current x squared, which gives us that standard geometry parabola. The next one, we're going to subtract, take the negative of that to flip it upside down. And then we're going to move it up to 4. And then we're going to move it over so it starts at 0. That's what those 4... that switch statement right there is doing right there. And then draw, this is just basically some like debug, showing what function is currently simulating right there. So let's go ahead and press F5. Okay, so this is the first function out of basic parabola. So I got it where you can press space to move to the next function. So basically this is, you can see right here, y equals 0. We got 80 pixels for 1 unit. We're going from a -4 to a +4, then a speed of 4 units. So I press space, and now we're going to see that y equals x squared, that happy smile face parabola right there. Press space again. Now we're going to get y equals -x squared. So that's basically turning the smile upside down. And the next one is -x squared plus 4. So we're going to move it upward, shift it upward 4 units. So it kind of reminds me of the old double dribble game where you shoot the basketball to change the game modes. And now to shift it to the right, we just change x, replace x with x -2. I don't know why it's -2, but you subtract off how far over to the right you want to move. So that will make it go from 0 to 4, go through the origin of the plane right there. Yeah, so that's basically four curves using just basic geometry, basic algebra. Okay, so here's the next one, a sine wave. Yes, on the left here, you got the basic sine wave, y equals sine of x. Starts at 0 and it crosses over the x-axis at pi 3.14. Then it crosses again at 2 pi 6.28. And it has a maximum of 1, amplitude of 1, and a minimum of -1. So if we want to take that and we want to get the same kind of maximum of 4, what we do is we just multiply 4 times sine x. So that'll start at the same 0, 0, then I'll go all the way up to 4. That'll be at pi over 2. Then come back, cross the x-axis at 3.14 right there. Then come down, get to a minimum of -4 at, what was that, 3 pi over 2. And then come back up at 6.28. So that's getting us kind of like the same curve that we saw with the standard y equals x squared. But what if we want this to start at x coordinate 0 and cross over at x coordinate 4? Well, what we need to do is kind of like normalize where it crosses. And how you do that, you can do y equals sine, and then in parentheses do pi times x. And what that will do is that'll make it cross the x-axis at 1, 2, 3, and 4. So for every unit, it's going to cross the x-axis. So it changes the x-intercepts to 1, 2, 3, 4, and -1, -2, -3, and -4. So if we want to change that, now we got it kind of normalized where it crosses over. But what if we wanted to only cross over at 4 and 8 and -4? Then what we want to do then is we do sine, then we do pi over 4 times x. That'll make it so it crosses over at 4 and 8. And then to get that maximum amplitude of 4 and lowest of -4, we just multiply all that by 4. So if we pull that into Excel, this is basically what it looks like. We've got our x, same kind of thing going on right here. Then sine of x, that's what we see in this first chart. Crosses at pi and 2 pi. And there's the formula right there. Then if we do 4 times sine of x, and it goes to a maximum of 4 and minimum of -4. And then if we do pi times x, then we get this one right here where it crosses over at 1, 2, 3, 4, 5, 6. And then the final one is 4 times sine of pi over 4 times x. So that'll get us the same maximum of 4, then cross over at 4. So in a little example program, we got screen sine wave right here. So we're going to start at -8, go to 8. We've got our x and y positions, x and y current, and then a speed and the current function that we're drawing. So yeah, on our update, we're just going to move x at a constant speed times our delta time, or game time dot elapsed time dot total seconds. That's what it is in Monogame. Then if our x is greater than the max x, and we're going to set x back to the minimum. So here's the 4 basic graphing, the 4 functions right here. So we're going to start out with math sine of x. Then we're going to do 4 times math of sine of x. Then we'll do math sine of pi times x. Then we'll do 4 times math f sine of pi over 4 times x. It's the same exact 4 functions that we looked at previously. Our draw is pretty much the same thing. It's just going to print out, display the current function, and the speed and the maximum. Not much really going on in draw. So to go between the different screens right there, just press enter. So here's the basic one right here. Here's our standard sine wave going. You can see it's crossing over at minus pi, 0, pi, 2 pi, and it has a maximum of 1 and a minimum of -1. And again, this isn't exact pixels. I had that conversion function in there to convert pixels to units. And that's why I recommend, like, trying to work in pixels can be, I don't know, aggravating at times. So sometimes just making a conversion function and using just like standard blocks or units is a lot easier. So pressing space, this is 4 times sine x. So multiplying by 4 gives us the max of 4 and min of -4. Still crossing at 0, pi, and 2 pi. Press space again. So this is sine pi of x. So this is going to make it cross It's kind of going to normalize where it crosses. It's going to cross over each unit. 1, 2, 3, 4, -1, -2, -3, -4, all the way up to 8. And finally, so this is kind of like our example function. It's going to cross at 0, go to a maximum of 4, then come back down at 4. Yeah. That's basically how you can modify a sine wave. So here's the next curve that I looked at. This is the type of curve that you'll probably want to use for jumping, which relies on physics, relies on velocity and acceleration to calculate the current position. There's two ways you can approach this. One, you can use like what I'm calling a continuous calculation. With that, you have to track the total lifetime from when the curve started to where it ends. If you don't want to track the lifetime, then you can use like the discrete values on each update. Yeah, so this is what it looks like right here. So the one in blue is the continuous, using the continuous function. The one in orangish color, uses the discrete value. It updates on every update, and you don't track the current time, the lifetime. So most game development environments and in real world, there's a gravity constant of negative 9.8 meters a second. I know Unity uses minus 9.8 meters a second. A lot of times you can go in there and change that, but I'm going to go ahead and use minus 9.8 for this example. So if we wanted to have a max height, like the character jumping, we want that character to jump 4 units high, then that'll be a max height of 4. That means our initial velocity has to be 2 times the gravity, which is 19.6. Because we want it to go up twice and then come back down. So yeah, looking at y0, here's the function right here. So we take the initial velocity, then add 1/2 times the current lifetime times gravity, and multiply all that by the current time, the current lifetime of the jump. So first one is like continuous. Get that second, we can calculate the height that projectile is at based on the lifetime and the initial velocity. And yeah, I just made a note here, keeping all the units straight. So our height is going to be like in meters. So we're taking the velocity, which is meters a second, times divided by seconds, minus the time times meters per second, which is the acceleration or deceleration, which is gravity, then multiplying that by time. So if you keep all your units straight, then it comes out to meters, and that's saved me quite a bit. Definitely back in my college days, if you can keep your units balanced, then a lot of times you'll come out with the right answer. I also had a note up here: distance is meters times seconds, velocity is meters per second, and acceleration is meters over second squared. I do have a chart here, which I got a lot of these values. I just broke it into tenths of a second, but in most game development environments, you're going to be doing 60 frames per second. So it'll be 60 instead of 10 right here. Yeah, so that's basically the continuous value. So the other method is doing like the discrete values. So I have that as y1. So to get the position, you take the previous position and then add the current velocity times the delta time, the amount of time that's passed since the previous update. And typically that will give you a really close curve, but it won't give you the exact values as you would had with the continuous function there. But I did find a presentation by a guy named Kyle Pittman called Building a Better Jump. If anybody wants to check that out, it's a good talk on just like the physics behind jumping. But there's a factor you can add to that. So if you take the previous position, add the current velocity times delta time, then add on 1/2 gravity times delta time squared. That will give you the same exact value that you would have gotten from using that first function, which I think is pretty cool. So you can get the exact same curve as you would have using by tracking by lifetime. But with this, you just take the previous value and can calculate the next value based on delta time and the velocity and the acceleration or deceleration, which is your gravity. So I have that right here. Add gravity times delta time to get new velocity. And then that will give you a curve that goes, which I have in this table right here. It will actually go from 0 to 2 times the acceleration in height. So they'll go from 0 to 19.6. But if we want that to go from 0 to 4, if we want to cap that out at 4, then we have to multiply by a constant, which is that value 4 divided by 19.6, which gives us 0.2041. Just know that it's a constant. They got to multiply if you want to max out that jump height, or that curve height. They'll give you the same exact shape of the curve, but it'll cap it out at 4. So that's what this conversion factor is. I have all this in Excel. But as always, the open source alternative, I believe OpenOffice or LibreOffice is still out there. Probably very similar to this. But yeah, there's my 2 charts right there. Our time going from 0 to 4. And right here, we're just setting delta time to 0.1. Got our initial velocity of 19.6, which is 2 times the gravity value, negative 9.8. So for each update, we're getting a new velocity. So when it reaches the peak of the curve, our velocity is going to be 0. Our velocity is going to be positive going all the way up to the peak of the curve. Then when it reaches the top, then it's going to have a negative velocity. And that negative velocity is just going to keep getting bigger and bigger until it goes back down to 0, height of 0. It'll actually be that negative 19.6 when it reaches the y value of 0. So here we have our y and y1. Like I said, y0 is using that continuous. There's a function right there if anybody's interested in that. But basically, this is calculating your current height based on lifetime and initial velocity. And then this next column, this is based on the previous velocity and delta time. So again, you got 2 different ways of calculating this. If I was doing a game, I'd probably use these y1, the discrete values, and just update the velocity and not worry about keeping track of lifetime of your jump or your whatever this curve is. And here's the conversion factor right here. This, like I said, just caps it out at 4. And you can see here y0 and y1, we get the exact same examples. And that is using that factor, that 0.5 times acceleration times time squared right there. I believe that's what it was. Delta time squared. Let's see here. Yeah, and I also mentioned that Unity provides a fixed update if you want your updates to be even, always the same amount of delta time between updates. I will also mention from that talk that I listened to that this method of doing the discrete values, it only applies if your acceleration is constant. So typically with gravity is always the same value. But I guess if you're doing something funky where the gravity changes or something, this doesn't apply. This is only for constant acceleration. And also I mentioned you could make gravity 1 unit a second, make things simpler, not use minus 9.8, but just know that a lot of game programming, well, at least Unity I know uses minus 9.8. So if you change that, then you're going to be, you have to go into your physics settings and all that. And there's tons of videos out there explaining the physics behind jumping and things like that. So I recommend looking into those if you want to know more. Like when you press the jump button, then it really accelerates faster or accelerates at a normal speed, then it drops off at a faster acceleration rate. This is just a simple parabola, which does pretty good. So here's the code for our physics implementation. We got our gravity minus 9.8, our initial velocity 9.6, our conversion factor, our current velocity, and current lifetime. Like I mentioned, I'm going to be showing the two different methods. If we're doing the continuous function, then we really don't need to worry about the current velocity. If we're doing the discrete values, we don't need to worry about current lifetime. But I went and put them both in here because I didn't want to make like two separate classes for each. Got our current x value. So again, the x value is just going to be a constant based on the lifetime. And then we only have two different functions. One is the continuous. So there it is right here, our initial value, our initial velocity plus 1/2 the lifetime times gravity, then multiply all that by lifetime. That will give us our current y value right there. Then in the discrete method, then I went in and checked because we're basing it on the previous value. So if there wasn't a previous value, we're not going to do anything. But our y is going to equal y current plus delta time times velocity, plus that factor, which is 0.5 times gravity times delta time squared. And that's to get a perfectly physics based position. Like I said, most games you probably just want to do delta times velocity, unless you need that actual a physically accurate value. You could just do y current equals delta time plus f velocity. But if you have a game you want to make sure your character is jumping can only jump 4 units high, then you need to add this additional component right there. But be aware you are doing a power, which you could, I'm using the math f.power function. You could just do delta time times delta time, which again is based on game time dot elapsed time dot total seconds. I don't know if this is any more efficient, more or less efficient than just multiplying that out. But you could just do delta time times delta time right there. The point being is like, yeah, that is a little bit of extra processing you're doing to get a physics accurate jump height right there. Then on every update, aside from just updating the current y value, we're going to update the velocity. So velocity is going to equal the current velocity plus delta times the acceleration, which is gravity, that negative 9.8. And here we're just adding, multiplying by that conversion factor to max it out at 4. And then here, like if the lifetime is greater than 4, then we're going to set it back to 0. And here we're just like, if we're changing the function to the second function, we're going to set the y to 0 and set the velocity to the initial velocity. That's basically it. This is just debug printing right here in the draw and drawing the dot to the screen. Okay, so here's our physics. So yeah, this is kind of like you can actually kind of feel it go up and slow down. Then when it reaches the height, maximum height of 4 at x position 2, then it's going to slow down and start falling. And as it falls, it's going to start accelerating again. So yeah, this is using the continuous function, using the lifetime and initial velocity. The other method is the discrete. So every time it's updating the velocity based on the acceleration and updating the y coordinate. So that's basically what it's doing right here. So I did put in the debug the current velocity, so you can see when it starts out at 0, you get 19.6 velocity. So that sends it upward until it reaches a velocity of 0. Then it starts falling back down. You can see the delta time right here is 0.0167, 60 frames a second. And you can see our current y value and that the converted factor. So you can see it starts out at 0 and starts slowing down when we get to 4. Then it starts falling and speeding up again until we reach y position of 0. Okay, so I did learn something new while I was preparing for this. All throughout, like school and college, I never really learned about. There's different ways to pronounce this: Bezier, I've heard Bezier. I think the most common one is Bezier curves, but I believe it's a type of a spline. There's multiple splines, and I really didn't look into splines, but I believe this is a special case of a spline. Basically, you got multiple control points. Typically, you have between 2 and 4 control. Typically, you only have 3 and 4 control points. If you have 2 control points, that's just going to be a line. So the first control point is going to be your start, and the second control point is going to be your end, and then you're just going to have a straight line, like an interpolated line, or points along a line between those 2 points based on time. And the time is going to range from 0 to 1. If you need it longer or shorter, you can multiply like by a factor, but typically we're going to look at 0 to 1. So if we want 3 control points, that's going to give us like a parabola or a curve that's not going to bend at all. It's just going to go up and down. So just like our previous examples, what we're going to do is start at 0, 0 and go up to 4, 2, or 2, 4, and then fall back down to 4, 0. So the first point is 0, 0. The second point is actually, I got the table up here. The second point is 2, 8. So your second control point is actually going to be a lot higher than where it tops out at. And then your third point is going to be the ending point. So here's the function down here at the bottom. So what I tried to do is for each control point, I made a different color. Like the starting point, I made red. The ending point's blue. That's your P1 and P2, or P1 and P3. And then the middle control point for the 3 control points is in green, this P2. And here's the math behind it. Here's the function right there. And I'll just, as with the physics, there's a lot of tutorials and videos out there on Bezier curves that are really interesting if you want to see how it's actually calculated. Basically, it takes your 2 points, and like with the third point, it draws a line from your first point to your control point, then from the control point back to your ending point, and then it takes like a chunk based on time, the distance between those 2 lines. And there's a lot of examples online that actually shows the curve being created. I'm not going to do that. That's already been done. I'm just going to show how you use this in a game. So here's the Excel spreadsheet right here, just showing what the values are. So here in these 2 columns, I have the 2 control points. That's the straight line right there, which I have graphed right there. Here's the one with 3 control points, which is our little parabola frowny face curve right here. And then the final one is 4 control points, which gives us almost like a sine wave. And I didn't get the exact right values here. I just kind of picked some middle control points. But yeah, looking back on the slide, this is the function for 4 control points. So like if I was doing like a train or something, then I could figure out where the train is, or a car is, or an enemy, flying enemies, something like that, based on the current time, what point on that curve it's at, using this function. So it's 1 minus t cubed times the first point, 3 times 1 minus time squared times time times the second point plus 3 times 1 minus time times time squared. That's a tongue twister. Times the third point plus times cubed times the fourth point. I'm not going to go into all the math behind that. Just know that's the function. And I don't know if I said it earlier, but 3 control points to the function is 1 minus time squared times the first point plus 2 times the 1 minus time times the second point plus time squared times the third point. I'm just saying this is because of calculus and derivatives. Or it might be Pascal's triangle. I don't know. I didn't get into all of the math behind that. If you are interested in knowing more about how to derive those values, there's plenty of tutorials and examples out there. So that's what basically this is, and here's the values in the spreadsheet. Looking at where is it? Bezier. Looking at the code right here. So got an X current, Y current. The current time is going to range from 0 to 1. So I'm just passing in control points, either 2, 3, or 4 control points. And here it is right here, setup points. Every time we go to a new function, we're just going to call setup points, give it a new list of points. So the first one is, I'm just passing in 0, 0, and 2, 4. So it's going to go from 0, 0 to 2, 4, or I guess that way. For the second one, I'm giving it 3 control points, 0, 0, 2, 8, 4, 0. So that's going to give us our frowny face curve. That looks like all the other curves that we did in the examples. And then the third one, we're just going to do the kind of sine wave type thing. We're going to start at 0, 0. We've got the control points 2.66 and 12, 5.33 and minus 12, and then end up at 8, 0. And I didn't have any mathematical way of choosing those middle points. I just kind of picked them just because they were in between the two others. So here it is, right here. Here's the update function. And those functions I was showing on the slide. Here's the 2. Here's it actually calculated for the 2 control points, the straight line. So that's your 1 minus f. 1 minus times the first point, x, plus times the first point x. So basically we're doing 1 minus times the first one, then times the first one, and adding those together. And we do the same thing for y. So the first line and the second line is exactly the same. We're just changing x for y. Then the second function, or the second function, basically using the 3 control points. This is just basically what I had on the slide written in code. Mathf.power 1 minus time squared times the first point 0.0x plus 2 times 1 minus times time times the second point x plus time squared times the third point x. And then we do the same thing for y. And here's the code for, again, I'll put all the code out in a source code repository and post a link. But for the 4 control points with the start, end, and 2 middle ones, this is the function. I'm not going to read all this, but it's like cubed. Same thing with cubed, multiplying by 3. But that's what it looks like in code there. So yeah, basically the draw is just putting out debug messages right there, and it's going to print out our control points. So here's our Bezier curve. So this is the one with 2 control points, 0, 0 to 2, 4. It's just going up and to the right in a line. Here's 3 control points. So this is our same. I'm not saying this is the exact same curve. It looks the same to me. You could probably do like a mathematical proof showing that this curve is the exact same as the original basic one that we did at the beginning, or the sine wave, limiting it to 0 to 4, or the physics curve. But yeah, again, this is moving at a constant constant rate in the x direction. So if you want to do something like a jump or something, use the physics. But if you don't just need a constant in the x, then you can do a BZ curve. And here's the 4 control points right there. So it's kind of the same thing, going from 0 up to around 4, so 3, something like that, crossing over at 4. So yeah, if I was doing like a car going along a path, I'd do something like that. And you can also do like loops with 4 control points. If you need a leap, use the Bezier curve. Bezier curve. And I think that's basically what I had on the last slide here. So applications for games: shooting a heavy projectile throwing a game, use a basic parabola. Wave projectile, sine wave, jumping, use physics, velocity, and acceleration. And if you're doing an enemy movement path or like train tracks, use a Bezier curve. Yeah, so that's going to wrap it up for Knox game design for July 2022. Yeah, it kind of was like math heavy. I just want to give a basic overview of the different types of curves, their applications, and how that's actually implemented in game. So appreciate everybody out there listening and watching. I'll plan on being back in a month.